Well, welcome back. We're going to be talking a little bit about simple machines. By definition, a simple machine is simple. Exactly. It really only does one thing, and it does it very well. A simple machine makes work easier to do. That's it. It's not complex. It's very simple, and it makes work easier to do. Before we get too involved in talking about machines, we have to go back a little bit and remember what work is, because we're going to be talking about how machines make work easier to do. We better remember what work is. Remember that work is equal to a force times a distance. So whenever a force moves through a distance, some work is done. And if we're going to make that work easier to do, we're going to have a machine that can work with a force and a distance. Move a force through a distance. Now there are two ways that a machine can make work easier. A, the machine can multiply an effort force to reduce the force necessary to do the work. And all that means is if you put a force into a machine, a push or a pull, a force, if you put a force into a machine, the machine can multiply that force, make it bigger, so on the other side of the machine you can move some heavier, larger object. B, a machine can increase the speed at which work is done. That means it can do the work faster, do the work in less time. So you want to remember two ways that a machine can make work easier to do. You can put a force in, and the machine can make that force bigger when the force comes back out the other side, or you can have a machine that increases the speed at which the work is done. The most commonly discussed machines are levers, inclined planes, and of course the wheel and axle. And in this little lesson we're specifically going to be talking about levers. There are three parts of any lever that you want to remember. Those parts are the fulcrum, the resistance arm, and the effort arm. So I've drawn a little diagram of a lever right here, and you can see I have it labeled R, F, and E. Well, a lever consists of a fulcrum, which is really a pivot point, and a board or rod that sits on top of that pivot point or fulcrum, and then you can set something that you want to move over here, that's the resistance, and then you can push down, that's the effort right here. E stands for effort, and when you push down with that effort, the resistance will move upward. The effort has a tendency to rotate around that point. The resistance has a tendency to rotate this way around the point. So you push down on the effort, the resistance goes the opposite direction. You push down with one force, and this machine is designed to do something with that force. And that's the general structure of a lever. Later on, we'll look at a couple of small levers. You can determine what class of lever you're looking at by remembering this, and there are three classes of levers. So to remember what class of lever you're working with, all you have to do is remember you can determine what class of lever you're working with by remembering this. Remember this little saying, FRE 1, 2, 3. FRE 1, 2, 3. If you can remember this, you will always be able to remember and identify the type of lever that you're working with. And there are three classes of levers: first class, second class, and third class. First class, second class, and third class levers. If we go back to this little saying right here, and we say FRE 1, 2, 3, what that really means is that in a first class lever, the fulcrum lies in between the other two parts of the lever. So in a first class lever, the fulcrum is in between the resistance and the effort. Remember the resistance and the effort? If the fulcrum is in between the resistance and the effort, then that makes this a first-class lever. First-class lever, the fulcrum, F, is in between the resistance and the effort. So you can identify a first-class lever. A first-class lever, if I draw a diagram of one, looks like this. Fulcrum, resistance, effort. The fulcrum lies between the resistance and the effort. Now in a second-class lever, the resistance is placed between the fulcrum and the effort. In a second-class lever, we can draw it like this. We're going to put the fulcrum on one end. We're going to have the resistance, R, between the fulcrum and the effort. And in this type of lever, what you'd wind up doing is putting something here that you want to lift. The pivot point, or the fulcrum, is right here, F. And you're going to pull up on this side of the lever in order to lift this resistance. In other words, you're going to apply your effort right here. And that's a second-class lever. The resistance is between the other two parts of the lever. The resistance between the fulcrum and the effort. See right here? In a second-class lever, the resistance is between the fulcrum and the effort. Now, a third-class lever. In a third-class lever, the effort is between the fulcrum and the resistance. The effort is in the middle, somewhere in the middle. In a third-class lever, the effort is between the fulcrum and the resistance. So we can draw a third-class lever like this. We have the fulcrum, we have the effort. We're going to pull up on the lever right there, and we're going to use that to lift an object that we'll call R, the resistance. So in a third-class lever, the effort is between the fulcrum and the resistance. In a third-class lever, the effort is between the fulcrum and the resistance. So, what do you need to remember? Well, remember that simple machines make work easier to do. Remember that work is a force, like an effort, that moves through a distance. Also keep in mind that there's two ways that a machine can make work easier to do. A machine can multiply the effort force, or it can increase the speed at which work is done. And remember that there are three very basic types of simple machines: levers, inclined planes, and of course the wheel and axle. Remember the three parts of the lever: the fulcrum, the resistance arm, and the effort arm. Remember FRE 1, 2, 3. In a first-class lever, the fulcrum is between the resistance and the effort. In a second-class lever, the resistance is between the fulcrum and the effort. And in a third-class lever, the effort is between the fulcrum and the resistance. Three classes of levers. Okay, now that we've come that far, let's take just a few minutes and talk about how you can measure the resistance arm and effort arm for any lever, because that's one of the things you'll have to do later on when we're talking about mechanical advantage. On a first-class lever, if you measure from the fulcrum to where the effort force is applied, that distance is the effort arm, the length of the effort arm. And one of the things you have to be able to do later on is compare the two sides of the lever. And so if you measure from the fulcrum to the effort force, we call that the effort arm. If you measure from the fulcrum to the resistance force, that's the resistance arm. And you notice that on this lever, the effort arm seems to be much longer than the resistance arm. So the distance from the fulcrum to where the effort force is applied is the length of the effort arm. And the distance from the fulcrum to where the resistance force is applied, that is the resistance arm of the lever. And it's like that for all three classes of levers. If we go over here to a second-class lever, if we measure the distance from the fulcrum all the way out here to where the effort force is applied, that entire distance is the length of the effort arm. And if we measure from the fulcrum to where the resistance force is applied, that distance is the length of the resistance arm. Over here on a third class lever, again the same thing. If you measure from the fulcrum to the effort force, that is the length of the effort arm. And if you measure from the fulcrum to where the resistance force is applied, that is the length of the resistance arm. So there's two arms for any lever. There is a resistance arm, there's an effort arm. And to identify them, you always start at the fulcrum and measure to the force. From the fulcrum to the resistance force, that's the resistance arm. And if you measure from the fulcrum to the effort force, that is the length of the effort arm. It works just that way for all three classes of levers. Okay, so here's a big question. How much does any simple machine make work easier? Well, that depends on something called the mechanical advantage, or the MA. Mechanical advantage, by the way, is just that. It's the advantage the machine gives you over not using a machine. So, the mechanical advantage of a machine can be estimated by first determining the machine's ideal mechanical advantage, referred to as the IMA. Ideal mechanical advantage. It's called ideal mechanical advantage because it only applies to an ideal situation where there is no friction. And generally speaking, that's not going to happen in the real world. So we're going to look at an ideal situation where there's no friction, there's no extra outside forces involved here. And we can use this ideal mechanical advantage to get a good estimation of approximately how much this machine that we're working with can make work easier. How much easier can it make the work? Well, ideal mechanical advantage can be calculated using the ratio between the input and output sides of the machine, the two sides of the machine. The input side where you put the effort in, called the effort side, that's the input side, and the output side, that's where you're going to move a resistance. We can call that R for resistance, just like we did before. So really you're going to be comparing the effort side of the machine to the output or resistance side of the machine. Ideal mechanical advantage can be calculated using the ratio between these two sides of the machine. So let's take a look at a machine, and we'll use a lever because that's what we've been talking about. So I drew a lever here, and you can see that the fulcrum, we'll label that F, it's right there, is in between the effort and the resistance, and the distance from the fulcrum to where the effort force is applied, the distance between where the fulcrum is and where you push on the machine, the lever, is 2 units long. And the distance between the fulcrum and where the resistance force is, the object that you're going to lift, is 1 unit long. You know, I'm calling these units. You can use any unit of measurement you want. You could measure it in feet, you could measure it in inches, you could measure it in centimeters, you could measure it in meters. Whatever the unit, makes no difference, because we're dealing with a ratio here, and the units are going to factor out when we do the calculation. So what I'm saying here is that in this particular first class lever, and we know it's a first class lever because the fulcrum is in between the resistance and the effort. We know it's a first class lever, and we know that the effort side is 2 times longer than the resistance side. We can use those measurements to calculate the ideal mechanical advantage. The ideal mechanical advantage is the input side, which is the effort side, divided by the output side, which is the resistance side. See the effort side and the resistance side. That's the input side and the output side. So it's the input side divided by the output side. And all we have to do is measure the two sides. We don't have to know what any of the forces are, because this is an ideal situation. We're going to make believe there's no friction. So if we have to, we can just measure the length of the effort side, measure the length of the resistance side, and compare them. Input over output. So the IMA is 2 units divided by 1 unit, and that gives us, when we factor these units out, that gives us 2. So what this is saying is that this machine, this first class lever, if we actually set this up, built it, and used it, this first class lever would multiply the input force, the effort force, by a factor of 2, making the work twice as easy to do. So it's twice as easy than not using a machine. It's going to multiply any force we put into it here by a factor of 2, thus making the work easier to do. So if we push down on this effort side with a force of 2 newtons, we'll be able to lift twice that, or 4 newtons, on the resistance side. If we push down with only 1 newton, we'd be able to lift 2 newtons. If we push down with 5 newtons, we'd be able to lift 10 newtons over here. So it multiplies any force I put in it by a factor of 2. Now, that's for an ideal situation. And I don't think that this lever would have a whole bunch of friction right here at this pivot point, but it probably would have a little bit. So the actual mechanical advantage probably would be slightly less than 2. But the ideal mechanical advantage is 2. So you can say that this machine would probably multiply any effort force by 2. But there is a trade-off. Though you multiply the effort force by a factor of 2, the machine divides the resistance distance by a factor of 2. Which means that even though you push down here with a force of 1 newton and you get 2 newtons of force out over here, you have to push this side twice the distance, and this resistance side will only move half that distance. So there's a trade-off. There's no such thing as a free lunch. You move the effort force through a distance over here, you only get half the distance out over here, but you get twice the force. And if you really stop and think about it, that makes perfect sense, because it supports the law of conservation of energy. Remember, we started out talking here about work consuming energy and being measured in the same unit, the joule. So force times this distance has to equal force times this distance. You can't increase the amount of work done. The work that you do on the effort side, the input side, has to be equal to the work done on the output or resistance side. So if this moves down 1 meter, this moves up half a meter. That gives us the same amount of work done on each side. It just decreases the force, makes the work easier to do. And that is how a simple machine works. And next we're going to talk about a couple of simple machines. We're going to talk about levers. We'll talk about inclined planes. We'll talk about wheel and axles. But in all situations, you'll be able to calculate the ideal mechanical advantage using the ratio between the input side and the output side, and you'll be able to figure out how much your machine will be able to multiply any effort force that's put into it. Okay, so what good is ideal mechanical advantage? Who cares? Well, nobody does unless you can use it in a real situation. So here's a real situation. I made a little lever here. It's a first-class lever. The fulcrum is in between the resistance and the effort. You can see that. And you can also see that the distance from the fulcrum to the resistance is 1 unit. That's the output side. And the distance from the fulcrum to the effort force is 2 units. That's the input side. And so when I calculate ideal mechanical advantage is input side divided by output side, which is 2 units divided by 1 unit, which gives me a mechanical advantage of 2. Now, the definition of mechanical advantage, ideal mechanical advantage, is that the ideal mechanical advantage tells you how much your effort force is going to be multiplied. So, if I take 2 units of force and put it here on the resistance, I'm going to use 2/4, then I should be able to lift those 2/4 with only 1/4 of effort force over here, 25 cents. And there it is. So that 1 unit is multiplied by 2, allowing me to lift 2 units of force over here. That's what ideal mechanical advantage tells you. Now, obviously, there's a little bit of friction in between the board and that fulcrum, but it's not really enough to make a difference in the real world. We don't have to worry about it. So that's how ideal mechanical advantage can be used to calculate the resistance force that can be lifted by any particular amount of effort force. In this case, we lifted twice as much resistance because the input side was twice as long as the output side of the lever. Okay, I made another little lever, and let's take a look and see what kind of lever I made. Now the rule here says FRE 1, 2, 3. So if I look at the fulcrum, it's over here on the left hand side, the effort's over here, so that means that the resistance is in between the fulcrum and the effort. Well, if the resistance is between the other two, that means that this is a second class lever. So with a second class lever, the resistance is between the fulcrum and the effort. And we can calculate the ideal mechanical advantage here. And we look at this, and the ideal mechanical advantage for any lever is always measured from the force to where the fulcrum is. From the force to where the fulcrum is. So we have 2 arms here. We have the input arm, which goes from the effort force to the fulcrum. In other words, the whole length of this piece of wood. And the output side of the lever, which goes from the resistance force to the fulcrum. And so we have the output side, the resistance side, is 1 unit, and the input side, the effort side, is 1, 2, 3 units. So the ideal mechanical advantage is input side divided by output side. So that's 1, 2, 3 units input side divided by 1 unit output side. That gives me an ideal mechanical advantage of 3. So any force that I apply over here, this lever is going to multiply that force by a factor of 3. So when I lift this lever, it's really easy to lift. I don't have to lift 3 units of weight or 3/4 worth of weight. I only have to lift with a force equal to the weight of 1/4, 1 25-cent piece. Because my ideal mechanical advantage is multiplying my effort force by a factor of 3. So it takes 1 unit of force to lift 3 units of force over here. That's how that little lever works. That is a second class lever. Now, another interesting thing to note is that even though the ideal mechanical advantage multiplies my effort force by a factor of 3, if I lift this effort force through a distance of 3 units, 1, 2, 3, then the resistance is only going to be lifted through a distance of 1 unit. And that keeps the work the same on both sides of the lever. Remember, force times distance is work. So whatever work I do over here by lifting it, I have to be doing the same amount of work there. This force times this distance equals this force times this distance. Just like that. That's the law of conservation of energy. So anyway, that's a second-class lever. All right, here I have made a third-class lever. And if you look at this third-class lever, you can see that at one end is the fulcrum, at the other end is the resistance that I'm going to lift, in this case a 25-cent piece. And between the fulcrum and the resistance is the effort. Well, that is exactly in line with what we see here. In a third-class lever, the effort should be between the other two, the fulcrum and the resistance. So, third-class lever. Let's go ahead and calculate the ideal mechanical advantage. The ideal mechanical advantage uses the input side, the length of the input side, that would be the effort side, divided by the length of the output side, that would be the resistance side. So, in this case, the length of the output side is from the fulcrum to the resistance, which is 3 times the distance from the fulcrum to the effort, which is the input side. So the input side is 1, the output side is 1, 2, 3. So when we divide the input side, 1, by the output side, 1, 2, 3, we get 0.3, or 1/3. So what that's saying is that this machine, this third-class lever, multiplies my effort force by 0.3. So if I put 1 Newton of force into the effort to lift this, I can only lift 0.3 newtons over here at the resistance end. So what good is that? I mean, isn't a machine supposed to make work easier? Well, it actually does. It all depends on what you want the machine to do. A third-class lever is very good at not increasing the force. It actually sacrifices force. But what it does is it increases the distance that that resistance moves. So if the effort moves 1 unit, the resistance moves 3 units. The resistance moves 3 units when I move the effort force 1 unit. So that's what a third-class lever is really good at. Third-class levers are all over the place. A baseball bat is a third-class lever. A broom is a third-class lever. A hockey stick is a third-class lever. So use a baseball bat, hold it right here on one end, you apply a force right here where my thumb is, that's the effort, and bang, that's a baseball bat. A broom or a hockey stick, just like that, the effort force is here, the fulcrum is here, and the resistance is what you're trying to move, either a baseball, dust on the floor, or a hockey puck. At any rate, that's a third-class lever. A third-class lever increases the distance through which the resistance moves rather than increasing the force.